In Lesson 106, Paul explained the operation of the HCSR04 ultrasonic sensor. Applying a minimum 10 microsecond pulse to the sensor's trigger pin causes the sensor to emit an ultrasonic chirp. Almost immediately, the sensor also sets the echo pin high to indicate that the ultrasonic chirp has been transmitted. The sensor resets the echo pin low when the chirp returns, having bounced off some nearby object. The pulse width of the echo pulse is a measure of the round-trip distance from the sensor to that object and back. Knowing the pulse width and the speed of sound, we can calculate the distance to the object. Paul demonstrated that µPython running on the Pico W is not able to generate a stable 10 microsecond trigger pulse. In Paul's demonstration, µPython generated a series of erratic pulses, most much longer than 10 microseconds. According to the sensor spec, 10 microseconds is the minimum trigger pulse width, so a longer, stable pulse should work. The unanswered question is, to what extent do erratic trigger pulses affect the accuracy and precision of the sensor readings? Sensor precision is the ability of a sensor to provide repeatable measurements under the same conditions. As a state machine program is more likely to produce stable 10 microsecond pulses, our assignment in Lesson 106 was to improve the precision of our distance readings by using a state machine to control the sensor rather than µPython. Sensor accuracy measures how close a sensor measurement is to the actual value. In this assignment, we will also try to improve the accuracy of state machine readings by implementing two techniques we've learned in previous lessons: low-pass filters and straight-line conversion. We'll start with a quick overview of a bare-bones µPython program to control the HCSR04. Imports and pin definitions have been omitted for the sake of brevity. Now, this may be familiar ground for many of you, so feel free to skip ahead to the state machine code part of the assignment. The program starts by ensuring that the trigger pin is low. In a while true loop, we set the trigger pin high, sleep for 10 microseconds, then set the trigger pin low. This should trigger the chirp and set the echo pin high. We wait in a do-nothing loop on lines 6 and 7 until the echo pin goes high, and then capture echo start time. Once the echo pulse starts, we wait in another do-nothing loop on lines 9 and 10 until the chirp returns and the echo pin goes low. Then we capture echo return time. Finally, we calculate the echo pulse width and the distance to the object. The loop repeats after a brief pause. Now, let's consider a state machine program that manages the HCSR04 sensor. It is relatively easy to set the trigger pin high for 10 microseconds in a state machine. A bigger challenge is how to evaluate the duration of the echo pulse. In recent lessons, we learned that state machines lend themselves to counting down rather than up. We will have to use the subtract-invert method of adding described in Lesson 90. There's a link to that lesson in the description below this video. Since we'll be counting down, it's prudent to start with the largest possible starting count, so our result never becomes negative. We know that state machine registers are 32 bits wide. The largest number they can hold is binary 32 ones. That will be our starting count. To minimize typing errors, we'll use the hex equivalent shown here. Let's look at a state machine program that controls the HCSR04. The @rp2 decorator alerts Thani that the following function is state machine code and ensures that the output, the trigger pin, starts low. Line 52 instantiates the state machine program, declares the trigger and echo pins, and sets the state machine frequency to 1 MHz. This means that each active state machine instruction will complete in 1 microsecond. As soon as we activate this state machine, it stalls on line 32, waiting for µPython to load a number into the TX FIFO. When the µPython program wants to make a measurement, it puts starting count into the TX FIFO. The pull statement on line 32 will move starting count from the TX FIFO into the OSR. Line 33 copies the starting count into the X register. The X register will be our counter. The set statement on line 34 sets the trigger pin high. This consumes 1 microsecond. The delay modifier, 10 minus 1, delays execution an additional 9 clock cycles. By the time we hit line 35, the trigger pin will have been high for 10 clock cycles or 10 microseconds. Line 35 sets the trigger pin low, completing the trigger pulse. The sensor will transmit the chirp, and the echo pin will be set high. The in underscore statement on line 37 copies 1 bit from the input pins, in other words the echo pin status, into the ISR. Line 38 copies echo pin status from the ISR to the Y register so that we can evaluate it. If the echo pin hasn't gone high yet, the jump instruction on line 39 sends execution back to the wait for echo high label. However, if the echo pin is high, execution will fall through line 39 to line 41, where we take another sample of the echo pin, copy it to the Y register, and check to see if it has gone low yet on line 43. If line 43 determines that the echo pin is low, it sends execution to the send loop count label. But if echo is still high, the jump instruction on line 44 sends execution back to the measure echo duration label, then decrements our loop counter by 1. When the chip returns, the echo bit goes low. Execution arrives at line 46, which copies the inverse of the loop counter to the ISR. Line 47 pushes the inverted loop count into the RX FIFO, and µPython will get the inverted loop count from the RX FIFO. Knowing the loop count, the number of active statements in the counting loop, the cycle time for each active state machine instruction, and the speed of sound in air, the µPython program can calculate the distance to the object. The other aspect of this assignment is the need to show improved precision when using state machine logic. We'll need a way to measure precision or variability. Standard deviation is a common method of measuring variability. The smaller the standard deviation, the more precise the process is. This doesn't necessarily mean that the readings are more accurate. Rather, it means that there's less spread in multiple readings of the same target. In this assignment, we'll set a target at 7 different distances from the sensor. At each position, we'll take 40 distance readings with µPython logic and 40 more with state machine logic. Finally, we'll calculate the average or mean and standard deviation for the µPython logic and state machine logic results at each of those 7 locations. The results will be saved in a comma-separated variable file for analysis in Excel. Using state machine logic should improve the precision of our readings. We'll evaluate a couple of options to improve the accuracy of state machine results. We'll apply a low-pass filter to the state machine observations, and we'll use a calibration curve to remove any bias in the sensor. This assignment is also the first time we've tried to pass control of a Pico output back and forth between µPython and a state machine. In our case, we'll be passing control of the trigger pin back and forth. I found that deactivating the state machine and repeating the object definition shown here put µPython in control of the trigger pin. Reinstantiating and reactivating the state machine put it in control of the trigger pin. Let's have a look at the program. As usual, this program starts with imports. We import pin because we're going to be using the pin statement, RP2 because we're creating a state machine, time because we're going to be calling time.sleep, and DHT11 because we're using the DHT sensor to temperature compensate the speed of sound. Here we declare the echo pin and trigger pin for the HCSR04 sensor and the data pin for the temperature sensor. Here we declare the echo and trigger objects and the sensor object for the temperature sensor. Here we declare the variable holding the number of active statements in our state machine counting loop, the low-pass filter alpha parameter, the slope and y-intercept parameters for our calibration curve, the file name for our sensor stats, the number of readings that we'll be taking at each position, the standard speed of sound in air, and the hex value of the 32-bit starting count described earlier. We will be running this program 4 times, once with no low-pass filter and no calibration curve, once with a filter, once with a calibration curve, and once with both a filter and a calibration curve. Each of the 4 datasets are stored in their own CSV file. We will adjust the alpha, M, B, and file name variables before each run. The M and B parameters will be derived from the unfiltered data using Excel. Here we tell Thani that the next function is actually a state machine program. This is the state machine logic that we reviewed earlier. The program pulls and copies the starting count into the X register. It sets the trigger pin for 10 clock cycles or 10 microseconds and waits for the echo pulse to go high, then counts how many loop cycles pass before the chirp returns and the echo pulse returns low. Once the echo pulse goes low, the inverted loop count is pushed to the RX FIFO so µPython can get it. Line 65 instantiates the state machine, specifying the trigger and echo pins and setting the state machine operating frequency to 1 MHz. After a brief delay on line 67, the sensor.measure statement initializes the DHT11's temperature sensor. As usual, the while true loop is wrapped in a try except clause. The while true loop begins by reading the current temperature, calculating the temperature compensated speed of sound, and messaging the user about the settings being used. The remainder of the while true loop consists of 3 nested for loops. The first for loop iterates target distance from 5 centimeters to 35 centimeters in 5 centimeter steps. For each target distance, we prompt the user to position the target and then press enter to begin measuring, or press Ctrl-C to quit the program. When the user presses enter, we enter the second for loop, which begins by setting the code variable to µPython. The code for loop starts by setting initial values for the readings and total variables used in the standard deviation calculations, as well as the min reading and max reading variables. It then messages the user. If code is µPython, we deactivate the state machine and redefine the trigger object to reestablish µPython control of the trigger pin. We then enter the sampling for loop. In the sampling loop, line 87 displays a progress bar. Lines 88 to 100 are the bare bones µPython code we reviewed earlier. Lines 101 to 106 calculate some sample stats. We sleep briefly, then take another sample at this target distance. When we have completed 40 µPython samples, execution falls to line 128, where we calculate the mean and sample standard deviation of those readings. We message the user, save the code variable, the mean and standard deviation values in the CSV file on the Pico. Once the CSV file is closed, execution goes back up to the code loop and code is set to state machine. When code becomes state machine, we reinstantiate and reactivate the state machine to reestablish state machine control of the trigger pin. Line 112 displays a progress bar. Lines 113 and 14 send the chirp and retrieve the echo loop count. We calculate the filtered loop count on lines 115 to 18. Line 119 calculates the distance to the target using the slope and y-intercept parameters from Excel. We calculate sample stats on lines 120 to 126, sleep briefly, then take another sample at this target distance. When we have completed 40 state machine samples, execution falls to line 128, where we calculate the mean and sample standard deviation for those readings. We message the user and save the code variable, the mean and standard deviation in the CSV file on the Pico. Once the CSV file is closed, the code loop is complete. The target distance increments and the whole process repeats. When the target distance loop is complete, the user is given the opportunity to start over or press Ctrl-C to exit. And here's how it all works. Sampling at each target distance starts when the user confirms that the target's in place by pressing enter. The program reads 40 samples using µPython logic, then 40 more using state machine logic. you can compare the behavior of the µPython and state machine trigger pulses on the scope. Watching all these samples being read would not be very interesting, so I've sped up this section a little bit. Even so, you can see that there seems to be more variability with µPython control compared to state machine control. At the end of each 40 readings, the code variable, the actual target distance, and the mean and standard deviation of the 40 readings are stored in a CSV file. We'll import that data into Excel to evaluate it. When we have measured all 7 locations, we set the low-pass filter parameter to 0.95 and run the test again. The results are shown on the left. Sample data is stored in a second CSV file for comparison to the previous unfiltered results. Let's look at the raw data first. We paste each CSV file into this section of the spreadsheet. The organized data section of the spreadsheet sorts the data by code type and then target distance. The spreadsheet calculates average standard deviations and average measurement errors for both code types. The upper chart plots standard deviation versus target distance. Red is µPython data, blue is state machine data. The lower chart plots measurement error versus target distance, and again, red is µPython data, blue is state machine data. Here we see the results of the first trial. This data is unfiltered and uncalibrated. On average, the state machine results have marginally better precision than the µPython results. But the state machine results show a significantly higher error than the µPython results. Comparing actual target distance versus measured distance, we can use the Excel slope and intercept functions to calculate the m and b values that will be used in our third trial. Based on raw data alone, the state machine code is marginally more precise, but less accurate than the µPython code. Let's have a look at the low-pass filter data. Here we see the results of the second trial. As described earlier, state machine data for this trial went through a low-pass filter. The standard deviation of this state machine data shows much improved precision compared to the first trial. However, the state machine results still show a significantly higher error than the µPython results. The low-pass filter improved the precision of the state machine, but did not improve its accuracy. Let's run the test 2 more times, once with a calibration curve and no low-pass filter, and once with both. Here we see the results of the third trial. As described earlier, the m and b values provided by Excel scale the distance measured by the state machine. This data is saved in a third CSV file for comparison. We run our last trial using the low-pass filter and the calibration curve and store those results in a fourth CSV file. Here we see the results of the third trial. This data is unfiltered, but the distance calculations are scaled using the m and b values we calculated earlier. The state machine precision is approximately as good as our first trial, but there's been a big improvement in accuracy due to using the calibration curve. Let's have a look at the impact of using the low-pass filter and the calibration curve at the same time. Here we see the results of the fourth trial. This data is filtered and scaled by the calibration curve. The state machine precision and accuracy are the best we've seen in this assignment. I think we can safely call this mission accomplished. We used a state machine and a low-pass filter to improve the precision of our HCSR04 results. We also used a low-pass filter and a calibration curve to improve the accuracy of those results. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.